In our last lab, we discussed Newton's 3 laws of motion and used dynamics carts to demonstrate those laws. Before beginning any experiment in the laboratory, be sure you are familiar with laboratory safety requirements. For a demonstration of basic lab safety rules, you can watch our video entitled Lab Safety. The 3 laws of motion also involve 2 other aspects of motion, inertia and momentum, which we will discuss in this lab. Inertia is the tendency of an object at rest to remain at rest, or of an object in motion to remain in motion. Inertia is an application of the first law of motion, which states that an object at rest will remain at rest, and an object in motion will remain in motion at a constant speed in a straight line unless acted on by external forces. You can feel the effects of inertia while riding in a moving vehicle, but the effects are most dramatic during the takeoff and landing of an airplane. Before the airplane begins to move down the runway, you and the airplane are at rest. As the plane begins to move, it rapidly accelerates for takeoff, and you feel as though some force is pulling you back into your seat. That sensation is a result of inertia. Inertia is not a force, but it feels like a force from your perspective. What actually happens is this. The plane rapidly accelerates down the runway, but as the plane moves forward, the inertia of your body resists the change in motion, and you feel like a force is pulling you back into your seat. Soon, the plane takes off and climbs upward. When the plane reaches its cruising speed, it stops accelerating, and you no longer feel the effects of inertia. With inertia in balance, you relax and settle into your seat to read a good book. Near the completion of your flight, the plane begins to slow down and descend in preparation for landing. As soon as its wheels are on the ground, the plane must quickly decelerate, so the pilot reverses the thrust of the jet engines. This action quickly slows the plane, and it seems to push you forward out of your seat. What actually happens is this. When the plane slows down, its acceleration is in the opposite direction as the direction you were moving. As the motion of the plane changes, your body, once again, resists the change in motion. Your body is actually moving forward faster than the airplane, so inertia makes you feel like you are being pulled forward out of your seat. When the plane comes to a stop at your gate, you no longer feel the effects of inertia. You and the plane are once again at rest. Momentum is closely related to inertia. Momentum is the tendency of an object in motion to remain in motion. Inertia exists whether an object is in motion or at rest, but momentum exists only when an object is moving. Momentum is difficult to describe in words, so physicists prefer to define it mathematically. To a physicist, momentum is the product of the mass of an object and its velocity. It can be calculated with the equation P equals m times v. Momentum is expressed with the units kilograms times meters per second. We can demonstrate momentum with a dynamics cart. A dynamics cart is a low-friction cart that contains sensors that measure its velocity, direction, acceleration, and other aspects of motion. The sensor data is displayed on a computer. This dynamics cart has a mass of 0.25 kilograms. A dynamics cart is equipped with a spring-loaded plunger that can launch the cart with a force of 1 Newton. We use the plunger to launch the cart. From the sensor data on our computer, we see that the cart moves with a velocity of 0.59 meters per second. We use this information to determine that the cart's momentum was 0.15 kilograms times meters per second. Momentum is an important factor to consider when two objects collide. Each vehicle's momentum is based on its mass and velocity. The vehicle on the right has a greater mass and velocity than the vehicle on the left, so it has a greater momentum. Since its momentum was greater, it changed the direction of travel of the other vehicle when the two vehicles collided. Sir Isaac Newton applied all three of his laws of motion into one law that summarizes the effects of momentum on two colliding objects. This is called the law of conservation of momentum, which states that when two objects collide, the total momentum of the objects before the collision is equal to the total momentum of the objects after the collision. We will use dynamics carts to test the law of conservation of momentum. For our first experiment, we set the dynamics carts at opposite ends of the track. Cart A has a mass of 0.25 kilograms. When two or more objects are involved in calculations, it is common practice among physicists to label the data with subscripts. A subscript 1, read sub 1, is used for data regarding the first object. So the mass of the first cart is labeled as m sub 1. When we launch cart A, it quickly reaches a velocity of 0.59 meters per second, which we label v sub 1. Here is a summary of all the data we have collected so far. Since we know the mass and the velocity of cart A, we can calculate its momentum, which we label p sub 1. We see that the momentum of the cart is 0.15 kilograms times meters per second. Here is all the data for cart A before the collision. The mass of cart B is also 0.25 kilograms. We label the mass of the second cart as m sub 2. When we launch cart B, it also reaches a velocity of 0.59 meters per second. However, the velocity of cart B is in the opposite direction of the velocity of cart A, so we assign a negative value to the velocity of cart B. For this lab, velocity toward the right will be positive, and velocity toward the left will be negative. The velocity for cart B is labeled v sub 2. Here is a summary of all the data we have collected so far. We know the mass and the velocity of cart B, so we can calculate its momentum, which we label p sub 2. Notice that the momentum is negative 0.15 kilograms times meters per second. The negative sign does not indicate negative momentum. It indicates momentum in the opposite direction. Here is a summary of all the data we have collected so far about both carts before the collision. The total momentum of the carts is the sum of p sub 1 and p sub 2. Since the momentum of each cart is equal in magnitude but opposite in direction, the two momenta cancel, and the total momentum before the carts collide is 0. Here is all the data from both carts before the collision. Now, let's see what happens when the two carts collide. After the collision, each cart reverses direction and moves a short distance apart. The velocity of cart A after the collision was 0.25 meters per second. But since the velocity was toward the left, it is negative 0.25 meters per second. The mass of the cart has not changed, so we can find the momentum of cart A after the collision by multiplying its mass by its new velocity. The new momentum is negative 0.06 kilograms times meters per second. Here is all the data from cart A after the collision. The velocity of cart B after the collision was 0.25 meters per second. Since the velocity was toward the right, it is positive 0.25 meters per second. The mass of the cart has not changed, so we can find the momentum of cart B after the collision by multiplying its mass by its new velocity. The new momentum is positive 0.06 kilograms times meters per second. Here is a summary of all the data we have collected. Now, we can calculate the total momentum of the carts after the collision. Since the momentum of each cart is equal in magnitude but opposite in direction, the two momenta cancel and the total momentum after the carts collided is 0. Here is all the data from both carts during this experiment. Notice that the total momentum of the carts before the collision was the same as the total momentum of the carts after the collision. This confirms the law of conservation of momentum. Let's try another collision with slightly different conditions. This time, we increase the mass of cart A to 0.50 kilograms. The mass of cart B will remain at 0.25 kilograms. We launch both carts with their plungers as we did in the previous experiment. Because the mass of cart A is twice its previous mass, its velocity this time is about 1/2 of its previous velocity, or 0.29 meters per second. With a mass of 0.50 kilograms and a velocity of 0.29 meters per second, we calculate its momentum as 0.15 kilograms times meters per second. The mass of cart B is 0.25 kilograms. Its velocity is in the opposite direction of cart A, so its velocity is negative 0.59 meters per second. Therefore, its momentum is negative 0.15 kilograms times meters per second. The total momentum of both carts before the collision is 0. Here is a summary of all the data we have collected before the collision. Now let's see what happens after the two carts collide. Both carts reverse directions as they did in the previous experiment. However, cart A moves at a much slower velocity of negative 0.13 meters per second. Cart B reverses direction with a velocity of 0.26 meters per second. Now we can calculate the total momentum after the collision. We see that the total momentum after the collision is 0. Here is a summary of all the data we have collected. Notice that the total momentum of the carts before the collision was the same as the total momentum of the carts after the collision. This, once again, confirms the law of conservation of momentum. In our next lab, we will continue our study of physics with demonstrations of wave properties. At this time, proceed with the corresponding activities.